To safely extract hydrocarbons, operators must predict precise fluid volumes and plan optimal drilling trajectories. But doing so requires solving a massive spatial problem. 99% of the target subsurface environment is entirely unsampled. The data we do have is highly polarized. On one end, we have borehole logs. These provide ground truth precision, but they are hyper-localized to a single vertical line, a one-dimensional pinprick. On the other end, three-dimensional seismic echoes provide wide volumetric width, but the acoustic data suffers from low resolution. The space between those sparse well lines is essentially a geological no man's land, characterized by massive uncertainty. Historically, bridging the physical gap between well A and well B relied entirely on a geologist's intuition. This manual approach yielded single, deterministic models that were highly prone to expensive drilling errors. This breakdown illustrates the modern approach. Instead of manual extrapolation, machine learning algorithms act as the deterministic bridge. They ingest historical data and rigid physical laws to map the unsampled space. By mathematically linking these sparse data points, AI shifts reservoir modeling from an interpretive art to a predictive science. It lays the absolute groundwork required to build a functioning digital twin. Constructing that digital twin requires moving systematically from macrogeology down to micro rock properties. It must be built in a strict, layered sequence. As outlined here, the workflow executes across 4 distinct stages: defining the structure, classifying the facies, mapping the properties, and finally calculating the volumes. Executing this pipeline is not a matter of running a single program. Each stage requires a highly specialized neural network architecture specifically designed to process complex multiphysics data. Mastering this layered AI architecture is the sole prerequisite for defining the actual commercial viability of the reservoir. The sequence begins with the structural model. This establishes the foundational framework of the reservoir and maps out the major geological faults. This stage was historically a massive bottleneck. Identifying and picking faults manually across vast 3D seismic cubes required months of tedious human interpretation. Today, operators deploy convolutional neural networks, or CNNs, to fully automate structural interpretation. These algorithms are pre-trained on thousands of established geological patterns, allowing them to scan raw seismic data and instantly recognize structural anomalies. The immediate operational benefit is a 500% efficiency gain. Massive seismic cubes are processed in hours rather than months, but the speed is secondary to the algorithm's actual resolution capabilities. Looking at this automated fault detection output, the true value becomes clear. The CNN reliably identifies structural breaks that manual picking misses, specifically sub-resolution microfractures. While these microfractures are invisible to the naked eye, they are critical to the model because they ultimately dictate the fluid flow pathways of the hydrocarbons. CNNs also excel at defining the complex, chaotic boundaries of underground salt domes, which frequently act as massive natural traps for oil and gas. By perfectly mapping these elements, CNNs provide a mathematically flawless structural skeleton, completely removing the highest layer of human visual error from the model. With the structural skeleton established, the next task is classifying the rock types, or facies, and mapping their internal properties. This presents the core physical challenge of subsurface modeling, converting an acoustic sound wave into a tangible physical rock measurement. This process is called intelligent seismic inversion. As this slide states, this is the foundational conversion, translating acoustic frequency directly into physical properties like porosity and permeability. To achieve this, the AI requires a baseline. It uses the physical measurements recorded in the 1D well logs as the absolute ground truth. The algorithm analyzes well data alongside seismic data, learning the precise mathematical relationship between the physical porosity measured at the borehole and the specific acoustic frequencies recorded around it. Once trained, the AI extrapolates. It applies that learned relationship outward across the entire three-dimensional volume, replacing acoustic echoes with hard physical data. The ultimate output is a highly dense 3D property cube. It maps porosity and permeability voxel by voxel across the entire geological structure. This property cube is exactly what allows operators to pinpoint the high porosity sweet spots capable of sustaining long-term commercial production. AI inversion is the only deterministic method available to directly translate blurry seismic echoes into actionable, high-resolution physical coordinates. Even with high-resolution coordinates, relying on any single deterministic 3D model still carries massive geological risk. The Earth is too complex for a single guess. To stress-test the model's assumptions, engineers deploy generative adversarial networks, or GANs. These networks ingest the physical laws and historical data and then generate hundreds of synthetic, geologically plausible variations of the reservoir. This is stochastic simulation. It shifts the workflow from single-guess modeling toward probability-based mapping. The AI cross-analyzes these simulated variations to determine the statistical probability of reservoir connectivity. If a high porosity zone appears in 99% of simulations, it is a viable drilling target. GANs replace human guesswork with rigid statistical certainty. They transform geological theory into a mathematically bulletproof investment model. That investment model leads directly to the final stage of the workflow, calculating volumes and establishing financial valuation. The master calculation for this valuation is shown here, STOIP, which stands for Stock Tank Original Oil in Place. The outputs generated by the preceding AI models, specifically the area, the thickness, and the internal porosity, feed directly into this equation with unprecedented, mathematically verified precision. This chart illustrates the advantage of scale. As the AI models ingest larger volumes of multi-physics data streams, the predictive accuracy of the final STOIP calculation increases exponentially. An AI-derived STOIP is no longer an educated estimate. It is the most reliable, deterministic financial metric an operator can present to a board of directors. Beyond financial certainty, this end-to-end multi-physics AI architecture drastically shifts operational cycle times. This timeline comparison demonstrates the efficiency gain. A legacy manual workflow that required 90 days to deliver a basic static model is now replaced by an integrated AI workflow that takes just 9 days. This dramatic collapse in time required happens concurrently with a massive increase in the granular detail of the reservoir mapping. Ultimately, the final deliverable is a dynamic, interactive digital twin of the deep Earth, allowing for continuous iteration. The defining operational advantage of this digital twin is simulation. Engineers can digitally drill the well and test thousands of horizontal versus vertical trajectories against the property cube to find the perfect path. Building the digital twin allows operators to perfectly maximize recovery. They resolve structural and financial uncertainties entirely in code, long before a single physical dollar is spent on